to see the campus, both with and without snow.
Oh yeah, she was. Mrs. Kenny was telling me that the campus is really nice.
Yeah, they're really nice.
Yep, they had really nice science.
Oh yeah, the science facilities are really quite
yeah.
impressive. So we arranged to take a tour of the science and meet the physics department chair and look at all the labs and both the research labs and the teaching labs. It's pretty cool. So that was very beneficial, and certainly for the equestrian programs that my daughter wants to go to, it's just perfect for her.
Yep.
So very positive. You know, sometimes you'll go on these trips and you'll think you want to go there, and you get there and say, this is not for me. Which is why we wanted her to go, you know, like, okay, you think this is what you want, let's go meet the people and look the place over and look at the program up front. And it all turned out real well. Okay, now, we have been talking about transition moment integrals. We've been looking at various exams and kind of getting ourselves set up to do that. And there's more of that to be done. So let's, without further ado, jump right into it and see what we have to do. And I think I can erase
We have all that if you want
all
to
this stuff. Okay, so let's just kind of get ready with some more stuff. Okay, today, oh my goodness. But 25 minutes ago, I was on my way up here to lecture, and Rod Soper said, "There's a leak down in the lab." Yes, I got pulled off of that, and then I get pulled off of this. It's crazy. Okay, today is April 12th, if you can believe this. You have less than a month of undergraduate school left. So pretty amazing. At this point, I want to retreat from specifics and just look at the quantum mechanics of a spectroscopic transition. The mechanism by which we understand the quantum mechanics of any spectroscopic transition, so this could be anything you could imagine, is to look at the transition moment integral. So we have an initial state, a final state, and a transition operator. And as we've mentioned in previous lectures, but we want to re-remind ourselves of at this point, as we get ready to look at more specific details, is the transition operator models a radiation molecule interaction, of which there could be many types. So basically, for this transition moment integral to be unequal to 0, that means it's allowed. The operator operator acting on the initial state must equal some constant. So it must be, let's see, now, I've never said this before, but hopefully this will make some sense to you. For this to be allowed, the operator operating on the initial state, in other words, the radiation interacting with the molecule, has got to take the final quantum state, and it can throw it in, can scatter into multiple quantum states. But there has to be a piece of this OI, a piece of this that is the final state of interest. There's something in this smashing against the initial state, you have to have a piece of it that gets in the final state. So if C is large, it's an intense transition. And what would you say if C were small? It's a weak transition. And if C equals 0, it's forbidden. You won't see it. Now, things can be essentially forbidden, and yet there'll be a small piece. So a lot of the problems we've been doing the last couple of meetings, looking at the exams to which you've been ball and chained into, present variations of this problem. What's the initial state? What's the transition operator? What's the final state? And we're trying to answer the question, if it's unequal to 0, it's allowed. If it's equal to 0, it's forbidden. And we're not really getting a sense of whether these C's are large or 0, but we are certainly getting a sense of whether it's 0 or non-zero. And this is the quantum mechanics of any kind of transition. We could go to nuclear physics, right down to biomolecules and everything in between. The transition operator is what's going to define what we're doing. So we have been doing problem after problem after problem with the transition operator. And we've also noted that our textbook, while a very good textbook in many aspects, really doesn't drive home the centrality of the transition moment integral. They kind of give you the results of it, but they don't show where it comes from. So there's good reason why it's not found so much in your textbook. It's the textbook is chosen to emphasize different things and kind of give you the answer to this for specific cases, rather than stand back in a general sense as we're always evaluating this when we're doing spectroscopy. Okay? Okay, that being said, let's take a look at some more of the problems that you're wrestling with on these exams. Okay? So if you could get out your assignments, let's see where we are here right now.
So for these transition moment integrals, I figured out what the minus e dot u vectors are for both of them, but I have no idea what to do with these as far as figuring out the transition moment integral.
Okay. So for you, okay, so specific example. So we have that our transition operator is minus, this is the electric dipole, minus the dot product of the electric vector times the electric dipole moment. And you have expressions for this now for various polarizations of light. Okay? So now what you need to do is form the integral. You actually need to do this. Okay, so we need to have so you have specific forms for the operator. Now we need specific forms for the initial and final states. And in the problems, I give some cases. Which one are you looking at?
5 or 6 and
Okay. And this is particle in a ring, right?
8.
Okay. So we have that's what we have, don't we? Okay. And we know what the initial and final, in the most general sense, there's an M initial and an M final. Okay? And am I saying that's 0 to 1? Oh, this is 1 to 2. Okay, so M initial equals 1 and M final equals 2. This is the 1 to 2 transition. And what do you want, left circularly polarized light or right circularly polarized light?
Let's do left.
Okay, so why don't you give me your expressions? Okay, so what is the form of the particle in a ring wave function?
It's going to be
1 over the square root of 2 pi e to the minus now, with this star, what do I do with the sign?
change it to minus.
Change it to minus, so that, and M final is 2, right? So it's minus I2 phi. And now I need the expression for left circularly polarized light.
Okay, so there's a x and a y component.
Okay, so that's fine.
Okay. Let's see. Okay. So it's going to be E0 divided by square root of 2. Times the cosine of kz minus omega t times e, little e, r cosine phi, or, well, e is in the electro.
That's not an,
Not
okay.
an exponential.
Is it the plus or the minus?
It is plus now because the negative cancels
Okay, so is this it?
out. No, it's the little e, like the charge on an electron.
Okay. Is it times this?
Yeah.
E to the,
Not e to the anything, it's just E is in.
Oh, okay, I get it.
Yeah.
Yeah, no, I get it. Okay.
Times R cosine phi. Okay. Well, that's the x component. There's also the y component where you change cosine to sine.
Okay. Is that it right there?
Yeah.
Okay. And this is over the square root of 2 pi. Okay, so this is an electric dipole operator. And I'm going to put this. I'm going to write E0 ER over square root of 2, E0 little e R. So this models the electric dipole interaction. And intuitively, if we had a charged particle going around in a ring, and we had a parallel plate capacitor hooked up to an alternating voltage source, we could flash these back and forth to keep this electron spinning around in the ring. So the intuitive model is the electric field. If it's coordinated and it's flashing, right now this would be driven down here, then back up, then back. And we could keep pumping it around just like pedaling a bicycle. Okay, so that's what this operator models.
Okay.
Okay? Now, we're going from M initial equals 1 to M final equals 2. The negative sign comes, as we mentioned earlier, from the star. Okay. Now, at this point, we have two terms. We have an R cosine and we have an R sine term. Okay. And what we need to do is evaluate the integral for both cases.
Yeah.
So for the cosine case and for the sine case.
Okay.
Okay? Or we can convert the integral to complex form. In other words, you could use the Euler, let me just show you something. The Euler relations okay, so those are the famous Euler relations. That we can use. And how would you like to pull a fast one?
Yeah.
Are you up for something really sneaky?
Sure.
You know, counting on the low strength of your moral fiber, I was hoping you'd say you'd want to do something sneaky and underhanded.
Yeah, I got no moral fibers, so.
Excellent. You're my kind of students. You know, these goody-goody two-shoes types just don't cut it with me. Yeah, we don't need those. It turns out that in a complex sense, we can represent circularly polarized light where the cosine is the real part. And this, we can put a factor of I right there. Kind of like that.
Okay.
Now, if I can do that with my polarized light, look at what that does for me. Don't I sound like Satan selling apples to Adam and Eve right now? Wow, you know.
Why are you allowed to just throw an eye in there?
Because I'm magnificent and powerful and worthy of being worshipped. I shouldn't push that too far. Okay, so the serious answer is in complex arithmetic. The x is often associated with the real part, and the y is associated with the imaginary part.
Okay.
Because complex numbers are effectively two-dimensional numbers with a real and an imaginary part.
Okay.
And it's common to have the imaginary part be the y or the sine piece, and the real part to be the cosine piece, as we see in the Euler relation. So that's kind of the answer. Okay, so we're going to pull out this from both expressions. And I put the E0, capital E0, little e r all together under the square root there. And I did it over here too. That r is going out. And now look at what happens. I get a cosine, let's see. I get
Don't you have two of those?
wait a minute, no, did I do this right? 'Cause this should be a cosine of phi. In your notes, was this a sine of phi? Okay, I was going along great guns.
It might have been sine, but we could be just imagining.
Yeah, I mean, there's
Let
a reason to believe mine.
me look and see what kind of crack I was smoking.
So that's, see, this is what you told us last. Right there. And that blue part.
Oh, okay, and I don't.
So it should be minus.
Okay, so LCP is minus.
Uh-huh.
Yeah. Okay, now. What am I doing wrong here? Well, I can do this. Let me do this. I'm going to take a different tack. Okay. Now I'm going to do, in the Euler relations, I'm going to solve these back into cosines and sines. Okay, so if I add these two expressions together up here, I get 2 cosine phi equals e to the I phi plus e to the minus I phi. And so if I add, if I subtract, I get 2 sine phi let's see, I get 2i sine phi equals e to the I phi. Oh wait a minute, I got these backwards. If I subtract, never mind. If I add these together, then if I subtract them, now I'm right, okay. So, e to the I phi minus e to the minus I phi. And this is sine phi equals 1 over 2i e to the I phi minus e to the minus I phi. And this is cosine phi equals 1/2 e to the I phi minus e to the minus I phi.
Plus e.
Oh, that's plus, sorry. Okay. Now, what that allows me to do is this goes in for this, and this goes in for that. Okay, now, what have you gained from that? Well, it turns out you've gained everything, because you have e to the I phi and e to the minus I phi. So you have 3 complex e to the things which we can readily evaluate. Okay, so let's take this term right here. We'll take the first term, okay? It goes in right here, and so we'll have 1/2 e to the I phi plus e to the minus I phi. Okay. And we've got all this here. So it's E0, little e r over the square root of 2 cosine kz minus omega t. Okay, that's that term. Then minus E0 er over the square root of 2 sine kz minus omega t. Now we'll put in the complex form here, 1 divided by 2 times the square root of -1 I e to the I phi minus e to the minus I phi. Okay. Now, how many integrals do we have to do?
1, 2.
You have to do 1 for e to the I phi, 1 for e to the minus I phi.
Oh,
You've got to do it again over here. There's an e to the I phi and an e to the minus I phi over here. But it's the same integral, isn't it?
It's exactly.
It's the exact same thing. In fact, if 1 is so we could, if you get the one over here, you automatically know what the one over here is. Does that make sense? So you can now, so we have, here's the final state, here's the operator, here's the initial state. And you're going to get integral, there's only two integrals that you're going to get. You're going to get the integral from phi equals 0 to 2 pi of e to the minus I to phi. And then you're going to get e to the I phi, e to the I phi, d phi. So that's the ones with the positive. In other words, what I'm selecting out, just so you can see it, I'm saying, look at this, and look at that. In other words, just take those three pieces out and integrate those. So what's e to the minus I2 phi times e to the I phi times e to the I phi?
E to the 0?
E to the 0, which is 1. So what's the integral from 0 to 2 pi of 1 d phi? It's 2 pi minus 0. That says that's non-zero. That's allowed. Okay? Now, are you comfortable enough to see what's going to happen with this one? This one's kind of weird. You have an e to the minus I phi. So this next little integral would be phi equals 0 to 2 pi e to the minus I2 phi e to the minus I phi e to the I phi d phi. Now, all those come out to what? E to the minus 3 phi plus 2 phi, it's e pi equals 0 to 2 pi of e to the minus I to phi d phi. Well, what is that integral? Well, is it at 1 over minus I to phi e to the I to phi evaluated between 2 pi and 0? Okay, so do you know what that integral is? We can do it. We can do it. We can do it. We can do it. Okay.
So is
Shouldn't it be e to the negative I2 phi?
Negative I2 phi. Yes, it should be. Okay. So
And is it supposed to be 1 over, should phi be in that coefficient?
it should not be. It should be minus I2, minus 2I. Okay. So this equals 1 over minus I times 2 e to the minus I 4 pi minus e to the 0. Now, guess what you're going to find out on this integral? What's e to the 0? 1. 4 pi is twice around the circle, so the angle is 0. Cosine the sine of the angle, the cosine is 1, the sine is 0, if we break it out like this. So this is also going to be 1, and guess what? That integral is 0. Okay? Now, if you're smart, you realize you have the same darn integrals over here, you don't have to do them twice. The end result is that this transition is allowed. Now, I feel like I did a horribly messy and disconnected job with that.
Just a tad.
So if you feel like it was horrible, messy, and disconnected, I agree with you. Now,
Did you jump back a problem, or are you still doing the same problem? For
no,
psi?
it's the same problem.
Okay.
Now, I think the hardest thing in doing transition moment integrals, or for that matter, any multi-step thing, is to kind of keep track of it all. It's what a bean counter, an accountant would do in a business, keeping track of all the sales and the taxes and the income and the outgo and the salaries. We've got a lot of stuff going on here.
Yeah.
And no one step is hard. It's kind of keeping all the steps organized is hard. And it's really hard to put it all on one whiteboard, even as big as this one is. Now, so let's kind of go back through it here for a second. Okay. So here's the general expression, right? There's an initial state, and there's a final state, and there's an operator. Then we have to specialize to our case. Particle on a ring wave functions are e to the I. So in general, they're 1 over the square root of 2 pi e to the I m sub l phi. When you do a star, I is always replaced by minus I. And we're going from m sub l equals 1 to m sub l equals 2 in this transition. Okay? So that's where this comes from. That's also where this comes from. So here's the initial state. Over here is the final state. In the middle, all of this in the middle is the transition operator O. And we got that last time. And it's an electric, but we can say some things about it. It's an electric dipole operator. So it should have the strength of the electric field, it should have a charge, and it should have a distance. It has all of those. But those are not going to figure at all in this integral, which is only an angular integral. They're just going to be constants. So in other words, you're not going to be integrating over z and omega t. You're not going to be integrating over r, because they are not in the wave function. So this whole piece, which I will circle now in red, so this whole piece, or in this one, this whole piece, comes out of the integral. Those do not figure in. And then, so what I said is, let's just look at these cosines and sines, which do fit in the integral, because they're functions of the phi variable. Let's see how they integrate out. And the one that is the plus e to the I phi gives a non-zero integral. The one that's a minus gives a zero integral. So we can basically say that this term doesn't contribute and this term doesn't contribute. Right, oh, there's a plus. This term doesn't contribute right here. Only the I-phi terms contribute, and they contribute as these integrals indicate. Now, I have some advice for you, and I think actually you're doing a pretty good job.
Good job, Cy.
You know, Cy, you are laying things out very in a neat and organized manner. It almost to do this, you'll get swamped in details if you don't figure out a systematic way to go through these problems. I mean, you literally get swamped in the details. And I guess this is the equivalent of having to go through the peptide cycle and the Krebs cycle and all this. You know, the complicated multi-step processes. And here you thought P-Chem was going to be beautiful and elegant and simplistic, and that there would be a few unifying equations and then it would all fall out. Now he's got that look of, oh crap, this may be worse than biochemistry.
Oh, it's definitely worse in terms of what you need to know, but I mean, you're not giving us an exam on all this. We're kind of working on all these with each other, so it helps out a little.
Okay, so what I want you to do,
Yep.
I mean, honestly, if you don't figure out a way to break it up systematically and keep track of the parts, it's virtually intractable.
Yeah.
It's too complicated to kind of work the way, you know, you're kind of used to a problem that takes half a page or maybe a page, and you can kind of neatly lay it out in a half a page or one page. This ain't it. And the key to seeing it is to take several pages and lay it all out. Now, some of the tricks of the trade are to use colors or to break it out into separate sections. But that's what you have to do. In other words, and it's trivial, but in a big thing that takes up the whole page, it might not immediately become apparent that this term can be pulled out of the integral. And that coefficients can be pulled out. It's not immediately obvious when those things have to be done. So, but what I would, you know, I'll do some things like I'll label this term 1 and this term 2, and then I'll do all of part 1 and have it over here, and I'll do all of part 2 and have it over here, and then I'll pull them back together. I did my PhD in quantum mechanics, and I had equations that would go on for pages, and this is the only way I could figure out how to do it, is to just kind of keep every piece organized. So it is a significant organizational problem. And interestingly enough, none of the individual steps are that hard. But you may not have encountered in the mathematical sciences something that was this long and involved.
Well, it's like when I was doing computer programming a few years ago, like, if you aren't careful with your organization, you'll never figure out where you went wrong.
Exactly right. It's just exactly the same.
Just too many moving parts.
It's exactly the same. And I had to translate all my multi-step things into a computer code. So you could mess up in the derivation, and then you could mess up in putting it into code.
Yeah.
And there were so many ways to go wrong, it wasn't even funny. So a lot of, you know, if you like the way I write on the blackboard, if you like the colored markers, all that came from, this is the way I'm gonna help organize things. And I would do a lot of organization by color.
Yeah.
Or spatial location. You break the problem up into pieces that are well identified. You do the individual pieces, you box the answers to the pieces, then you assemble the answers. It's probably different from anything you've done in mathematics or chemistry up till this point. And it's not that I'm trying to trick you or give you ultra hard things. It's we've kind of arrived at a point where you have to be comfortable handling this level of difficult. See, you came in here, I don't know what to do next. The trouble is there's too many big pieces floating around for you to easily see what to do next.
Yeah, and if I messed up any of it, I would have messed up the whole thing.
Exactly right. So this is always what we're doing. So that you can remember that. And then there's the initial state and the final state. Boom. The star can be very important. If you miss the star here, it's a disaster.
Yeah.
Okay. And then you have to get the operator right. And away you go. So, do you guys feel good enough about this one to try to get this one problem done so I could look at it to tell you whether you did it right or not?
I think so.
I think you're pretty close. Ed, what about you?
I hope so. I think I can.
Okay, I think it would be a wonderful exercise if you were to take this very problem and work out all the pieces. That would be enormously helpful.
When you
Yeah.
say work out all the pieces, because we already kind of went.
We've essentially done it, but you lay it all out. In other words, I've had to compress, and I've gone here and there, and you know, I kind of want you to take what's on the board and really clean it up, and really show me all the pieces of the problem. Okay, let me take a look here. Now, the deal is, okay, the deal is, as we mentioned the last time, you should be able to do a whole, if you do it for LCP light, you can immediately get it for RCP light.
Yeah.
Number 10, I can show you in our next meeting. We had just started to work on 10.
What's number 10?
It's a particle in a box one with a different transition operator. That one's actually a much cleaner problem than the one we're beating through right now. One-dimensional box of length L, you're going to calculate.
Did you give us that handout? is C handout of symmetric limit particle in the box.
Have I given you the symmetric limit particle in the box? I can't remember.
I don't think so. Oh, it doesn't sound familiar.
I don't remember anything about a symmetric limit.
Okay, I have a whole. Okay, let me re-give it to you. If I may, or I just honestly can't remember
Okay.
whether I gave it to you or not. If you do it over symmetric limits, it's from minus L over 2 to plus L over 2, rather than 0 to L.
Okay.
But there are some significant advantages to doing it over symmetric limits that I can show you in this problem.
So minus L over 2 to L over 2.
Right. Uh, let me show you what the deal is. It's a. I assume that either on the video or in photos you got what was on this board.
Oh, everything's there, yeah.
Okay.
Found out my fiance got accepted for a transfer to University of Utah.
Okay, where is she now?
She's here, but since that's where I'm going to be going, she's transferring there.
Dude, nice.
Yeah.
And now, what is she still finishing her undergraduate?
Yeah, she has one more year.
And
but,
what's her major?
Psychology.
Oh, yeah, she should be able to.
Yeah. Yeah, she's probably going to take more than a year because, you know, she's been doing like way too many classes at once and it's just too much for her. So maybe like 3 more semesters.
But you'll be there.
Yeah. Yeah. Yeah, there's no hurry with me, you know, 5 or 6 years there.
Yeah, exactly.
That's so long, man. That's crazy.
Yeah.
Get it, Sai.
But you know what? If you don't watch it, you'll drift along for 5 or 6 years.
Oh, no, I'm not saying like it's like a commitment. It's a good commitment to take for sure.
Yeah.
But it's a long road. There's no doubt about it. And I tell people, unless you really want that PhD, you're going to find the path too long, too steep, and too hard to do it.
But does it not change a little? Because when you're in your undergraduate, like we're sitting here learning multiple different concepts, and then is he going to be specifically kind of
You'll be much
one?
more focused.
Yeah.
You know, you might be combining several different kinds of science classes.
But they're all really relevant to each other, right?
But you're combining them in such a way to advance your research.
Yeah.
So they're all in that sense related and relevant. In an undergraduate degree, the challenge is, particularly in your junior or your senior year, you kind of are interested in chemistry or biology or physics or a combination of those. And, you know, world history is fine, but you want to know what these electrons are doing.
Yeah.
You know?
Yeah.
Okay. Let's say we have a particle combined on the x-axis to move between minus L over 2 and plus L over 2. Okay. So that means the wave function, which is a cosine kx plus b sine kx. And let, you know, the usual thing, the potential v of x equals 0 between minus L over 2 and plus L over 2. And infinity outside. Typical box conditions. So now let's do boundary conditions. So psi k of x has to be equal to 0, or just psi of x has to be 0 when x equals L over 2, or x equals minus L over 2. Okay? So this says a cosine k L over 2 plus b sine k L over 2 has to be 0. Okay, so let's take each one in succession. Okay. For the cosine, this has to be m pi over 2, where m equals 1, 3, 5, 7, 9. In other words, if you want the cosine to be 0, it's got to be a multiple, an integral multiple of pi over 2, and it has to be an odd multiple. Okay, if you want the cosine to be 0. So you can have psi m of x equals 0 when x equals m pi over 2, m equals 1, 3, 5, 7, 9. Okay, so that says that k, okay, so what does k equal? K equals 2 over L m pi over 2. I'm solving for this expression. K equals 2 over L m pi over 2. Notice that this happens. K equals m pi over L for this one. And under these conditions, b equals 0. Now, how do you get the sign to be 0? K L over 2 has to equal m pi, where m
It's 1, 2, 3.
equals what? 1. Now you already have all the odd quantum numbers.
Yeah, why do you have only odd quantum numbers there anyway?
Okay, because the cosine only works with 1, 3, 5, 7, and 9. Oh, wait a minute, did I do this backwards? Yikes, I did it backwards. No, I hold on. Cosine is always 0 at pi over 2, so I did it right.
Yeah.
Okay, now, how do I make the sine go to 0?
We
Doesn't
set it to
that-
pi.
Is that m pi?
M pi, yeah.
Okay. And m.
Can you equal any real whole number though, right?
Yeah, no. What am I doing wrong? Oh, okay. Take multiples of pi over 2. the sign goes to 0 when m equals 6, 8. In other words, if you have an even number here, and we'll throw the m equals 0 one away. If I have an even number there, KL over 2 equals m pi over 2. Okay, and in which case, K equals, again, m pi over L, but with even quantum numbers. I want the same argument in my function. So in other words, the boundary for a symmetric particle in a box, the energies, you have two forms of the wave function. Okay, and for the sign, it's m equals 0, 2, 4, 6. And for the cosine, it's 1 over the square root of 2L cosine m pi x over L. M equals 1, 3, 5, 7, 9, and so on. In other words, when you go over symmetric limits, your wave functions are either going to be sines or cosines.
Okay.
They're going to alternate in their energies. So you're going to have the same energy function. Now I have this handout that goes through this whole derivation. I just wanted to show you the essence of the derivation. Do you see what I'm doing right here? I'm forcing the wave function to go to 0 at the boundary. And that induces a quantum. Whenever I force a wave function to conform to a boundary, I put constraints on the wave function. And in other words, if I want this to go to 0, to have non-zero A, KL over 2 equals m pi over 2, where m equals 1, 3, 5, 7, 9. If I, and then for that one, B equals 0. If I want this one to be non-zero, KL over 2 has to equal m pi over 2, where m equals 0, 2, 4, 6, 8. If you'll recall, we can throw the 0, 1 away with other considerations. Okay. Now, these wave functions look identical to the ones we have. They're just shifted to be symmetric about the origin. They have exactly the same energies. Now, why did I want a symmetric wave function? If this is something we go over in molecular spectroscopy. What do you know about this function? What is the integral of that function over symmetric limits?
0.
That's right. I mean, that one is 0. Okay, now, what is the integral of this function over symmetric limits?
Not 0.
That integral is not 0. Okay. In other words, functions are even or odd. So an odd function, let me get these. An odd function is one where, let's say this is x, and here's minus x. These have equal magnitudes, opposite sign. That's an odd function. An even function, we have the same value. So even functions over symmetric limits have non-zero integrals. Odd functions over symmetric limits have, even functions have non-zero integrals. Odd functions always integrate to zero. So it turns out, so this is an even function, right?
Mm-hmm.
That's an odd function because this is down and this is up and the integral cancels out. Now, why do I care so much about even and odd functions? I can, by symmetry, tell you whether the integral is zero or not, and I don't have to do the integral. That, by the way, is one of the big things in molecular spectroscopy. We're going to use symmetry properties to tell whether transition moment integrals are zero or non-zero.
And is this related all to the problem number 10?
Yeah, this is problem number 10, because we can figure out that we can figure out whether the integral is zero or non-zero just by multiplying things together. Okay, now here's some rules. Even times even equals even, and odd times odd equals odd. Oh, excuse me, equals even, and even times odd equals odd. You need to know those three rules. Now, with those three rules, we're going to evaluate the symmetry of the initial wave function, the symmetry of the transition operator, and the symmetry of the final wave function, and we won't have to do the integral. We'll know right then and there. So, basically, I've laid the whole groundwork for us doing and completing problem 10.
Okay.
Now, do you guys remember much about even and odd functions?
I don't remember anything about it.
Okay, and how many calculus courses did you take?
2.
I took all 3. I don't remember ever learning about even and odd.
They might not have talked about them.
Yeah, it doesn't really ring a bell for me.
Yeah, I mean, it's possible that was not among the topics. But the group theory, the molecular spectroscopy class, you're learning a lot of that group theory. It's a generalization of the idea of even and odd functions.
Yeah.
In other words, group theory takes even and odd, the idea of even and odd functions, and just ramps it up to a whole new level. So
No, I know. They were talking about it.
and they do some example, and I can show you the molecular spectroscopy book, and we can actually give this to him. So we've kind of laid the groundwork for doing problem 10, which is a much simpler problem computationally than problem 9.
Okay.
Okay, believe it or not, you're almost done with 10. Absolutely. Okay, now let's look at part A and B of number 10.
Okay.
Qualitatively, by symmetry, noting that the symmetries of the electric quadrupole tensor operator and the initial final particle. Draw appropriate diagrams for the wave functions and the operators, and use the theory of even and odd functions to determine whether or not their transition moment integral is 0. You're going to draw pictures and be done. You're going to love it. Okay.
I just don't get where the picture comes from.
Yeah.
Like.
Yeah, and it's the wave functions and the operators.
Okay.
Okay, now, since you asked, I'm going to provide a special customized view.
Are we on a time crunch or are we good?
We're good for about 5 more minutes.
Okay.
Are you good for 5 more minutes?
Oh yeah, definitely. I was just wondering if we're gonna be staying in here instead.
Now we should just keep working on exams.
Okay. So, what we have, let's say this is the x-axis.
Mm-hmm.
What does the line y equals x look like?
Just go straight through the middle,
Okay.
like that. Yep.
Is that line an even function or an odd function?
That looks like it'd be an odd function.
That's correct.
You just deal with that.
Because, okay, now I want to know about this parabola.
That's even.
I want to know now about what's that one?
Oh, that's odd.
You sure they didn't teach you this stuff?
Okay, now let's see if I can do one more in here. Got red. Oh, blue.
The only thing I'm noticing from this even odd thing is it seems like you're taking into account that below the x-axis is a negative, and you're just canceling them out.
Well, yeah, and I'm gonna see if I do an integral. If I integrate from here to here over symmetric limits, the negative area is going to cancel the positive area.
Yeah.
It's going to integrate out to 0. Okay, now, what if I do
That's still odd, right?
odd? That's right. Now, what if I do an even function times an odd function?
Well, negative times a positive is a negative. I don't know how I'm correlating that. It's going to be odd.
Okay, so if I multiply this times this,
You'll get an odd.
so
No,
in other words,
even.
here let's say y equals x, and y equals the sine of x,
Through one.
or let's say let's say z equals the sine of x. So y times z equals x sine x.
It's even, right?
Okay, which is an even function. So what does it look like?
I don't know. X sine of x.
X sine x. So we know sine x is odd. We know that. So what does x sine x look like? That's a very appropriate tool to pull out at this point.
It is a beautiful M.
Exactly right. Here's x sine x.
Okay.
Okay. Now, what's x cosine x?
X cosine x?
Mm-hmm.
I feel like it'll just.
Even or odd?
That is odd.
Exactly right. Let's show. Here's x cosine x. Actually, these calculators are wonderful for teaching about even and odd functions.
Yeah.
Okay, so are you starting to get the picture?
Yep.
Okay, now.
What is the point of using this?
Okay, now, are you ready for the point?
Yeah.
Okay. What if I have a transition moment integral one over the square root of 2L sine 3 pi x over L. Then I have x to the fourth is my transition operator. 1 over the square root of 2L. The sign should be an even number, actually. 2 pi x over L. And we're going to do cosine 2 pi, or cosine pi x over L dx. So this is the initial state, this is our operator, and this is our final state. Do you see how I've broken apart a transition integral into 3 pieces? Now, why don't we just say, we're just going to say 2 pi over L equals 2, and pi over L is going to equal 1. All right?
Mm-hmm.
Now, I want you to multiply sine of 2x times cosine of x times x to the fourth and graph it on your calculator.
Okay. Sine of 2x times cosine of 2x?
Okay, no, it'll be sine of 2x
Yeah.
times
The cosine.
cosine of x times x to the fourth.
Cool.
And we're going to graph the function.
Whoa. It's going crazy. Should I spread it out a little? Zoom out?
Okay, now,
Or is that okay?
you've seen enough. Tell me what this function's doing. Is it even or odd?
To me, it looks like it's odd.
That's right. And we could have predicted that because this is even. X raised to an even power is even.
Yeah.
Okay. Sine 2x, sine of 2x. Okay. What is that? Now let's see, all the sines,
You're just doubling it all.
the sine is odd, and the cosine is even. And what's even times odd?
It's odd.
Odd. What is your graph?
Odd.
Odd. So he graphed this, and you can see right by the origin, it's clearly an odd function. Okay? Now, would you rather do that freaking integral or know that it's 0?
That's a pretty good way of doing things. Even, then you'd have to do it, right?
If it's even, you know it's non-zero. That's sometimes
That's
all you
need to
want.
know. That's true. Okay.
Okay? Like, let's say you have a rule, you won't marry any Jewish or Muslim girls. Okay?
Yeah.
And you find this really cute, rich girl, and her dad's a multimillionaire, and she's smart and good looking and nice, and but you have the no Jews and no Muslims. Not that they're bad, that's just not what you want, right? And then you suddenly find out she's a devout Christian.
Ooh.
You say, that's a non-zero transition moment integral. That's all you need to know at this point, right?
Yeah.
And you call her up. Can we go get caught? Okay. I gotta put this in terms you can understand. So sometimes it's just enough to know that the integral will be
Zero or non.
This one is by symmetry 0. So if this were your initial state, this were your transition operator, it would never give you a piece of that final state. The integral would be 0. This is why we do molecular spectroscopy the way we do. Because we can show you, I can generalize this idea and show you in all sorts of situations whether we expect something or don't or not.
Yeah.
All right? So you guys really have the hand, you can now probably do problem number 10. And you can just graph the functions on your calculator.
So you pretty much just got to set up the integral and then see if it's just a non-zero.
Yeah, see whether it's even or odd.
Okay.
Well, what's part B?
Actually do the integral.
B, formally, quantitatively, by a formal evaluation of the transition moment integral. I'm making you do it both ways.
Okay.
But I think a glimmer started to appear here on this one.
Yeah.
Yeah, I'll get back to you on Thursday with how we did.
Okay, now, believe it or not, you are going to finish all these tests, and you're going to really know this stuff. This was a transitional lecture. I mean, we really started to show you what was happening. And as soon as you get the idea, it'll all follow. And we're almost here, right here. You almost have the whole banana. Let's stop it.